This is the result of the wave of excitement created by the discovery of the ringing of the bell, namely the gravitational waves. I would like to introduce you to the panelists with great pride. Professor U.R. Rao, eminent space scientist, is the chairman of Bangalore Association for Science Education, which is administering the planetarium.
I consider this a very important event because we rarely honor our own people. And this is something, of course there are people who are honored because they got large number of papers. But in the scientific world, it is not the number that matters, it's the quality. You may have one good quality paper for a life. Now, of course, since the space age began, as you all know, there has been practically a great discovery, every alternative. It's earth-shaking. Starting with, from the very beginning, we had absolutely starting with the quasars, for example, then followed by solar wind coming in, followed by the X-ray astronomy, and the pulsars, and so on. And X-ray astronomy started, of course, with that. When you started finding X-rays from neutron stars, and then also from that's how the black holes were discovered, where the X-rays were coming in, and black holes became. Now, black hole has always been a very important thing because it was in the scientific field, but it was never seen. Of course, obviously we can't see. But on February, many papers were written before that. On February 11, 2016, one of the most important things this time is rarely you hear, every year one used to get a new, but rarely one hears a great discovery of this type, the gravitational waves were discovered. And this was waiting, the two black holes coming together and merging together and forming, giving out gravitational waves, and this is something very, very exciting, and these were discovered. Now when you go back, one wonders sometimes, I think it was more than 50 years ago, there are many who have been writing about it. Dr. Vishweshwara, his first paper was in 1960 68. Was in that, he wrote a paper. At that time, of course, even black holes were just coming into picture. And there he said, what happens when the black holes collide, and how the gravity waves will be formed, and how they can be detected, because this is fundamental to even the existence of Einstein's theory. And absolutely fundamental, because you see, up to the black hole, yes, then what happens when beyond the black hole, when the two of them come together, then they obviously will get into one. Then what happens? Then such a thing must produce enormous amount of energy. How does the gravity waves come from? And what do they create? And around, I think it was about 10 years later, I don't know, your first paper was 75 or 70, I verified it. This number, 75, yes. And these were proven. And fortunately for us, that even in this announcement was made, these two papers were cited by many people, that they were the ones who started the thing. And I don't want to talk more about the subject, because they are the authors, and they are the ones who thought of these things well before the discovery of black hole itself was made. And I am great pleasure in introducing Dr. Vishweshwara, who has been with this the planetarium from the very beginning. And Dr. Bala here, he is also a member of our board, and I am so happy. And also Bangalore must realize that, look, there are planetariums and planetariums. And of course every planetarium has a board. But which board has such halls, stalwarts like this? To show me one board in the country, a planetarium country, having great pleasure in introducing Dr. Vishweshwara.
He is going to describe the discovery of the waves to you, and he is the founder director of this planetarium. and we are very happy that he has been associated with us from the day of inception.
General theory of relativity, a theory unique, unprecedented, and people like J.J. Thomson have described it as the most beautiful creation of the human mind itself. So that was last year, and no other theory has ever matched it and probably never will match it. But then that was 2015, was the centenary of Einstein's general theory of relativity, which brought to the fore the notion of space-time. And then in 1916, exactly 100 years ago, I mean, he was an incredible man. He himself predicted, on the basis of general theory of relativity, that there should be gravitational waves, which we are talking about today, the ripples, as they say, in space-time. So we know that sound goes through, otherwise I won't be talking to you and you won't be listening to me. Light, electromagnetic radiation, through which we see everything. And finally, nobody had thought of this gravitational radiation, a new kind of radiation which travels with speed of light in vacuum. This was already given by Einstein. But how does it produce? Any mass motion like this, what I am doing, will produce gravitational waves. It is so weak that you don't feel it. If you had felt it and if you had resonated it, if I do this, you would also be doing this. That would be terrible. Okay, when you go to a dance performance, you will also be dancing. That won't happen. So gravitational wave is so weak. Then Einstein had given this and how it is produced, everything. Therefore, they wanted to find gravitational waves terrestrially in the lab, and in 1966 or so, 50 years after Einstein's prediction, I happened to be in the University of Maryland and working, fortunately, as it happened, on black holes. Many of my co-students were doing on other things, but it fell to my good fortune to work on black holes. And at the same time, we had this Professor Joseph Weber, who wanted to detect gravitational waves. He was a pioneer. Even today, when LIGO has succeeded in finding the gravitational waves, they always say that the inspiration came from Joseph Weber, although unfortunately he was not able to find them. He felt that he had found them, but statistics and all that didn't work out. But he was a great inspirational person. There is a whole story there. Someday I will tell you, or I will write about it. Then, so it was not possible. At that time I wrote 2 papers. First, as Professor Rao kindly told you, first was on the structure of black holes, and secondly on the stability of black holes, which is very important, because unless something is stable, it won't have any existence in nature at all. One thing is, for example, Humpty Dumpty sitting on a wall is an equilibrium state, but you nudge him, he falls, and he won't exist anymore. Not all the king's men and all the journalists can put him together, so he won't have stability. Therefore, stability of black hole was very important. And the third question, obviously, that comes, how do you see the black hole? See within quotation mark. And I thought the only way to do is send in gravitational wave pulses, sharp pulses, and that's again another story. And lo and behold, out came what came to be known as quasi-normal modes, and now it is called the ring down of the black hole. First I will show you the streaming, that 11th, what they told you, and then I will show you what had happened. That is, how many billion years ago? 1.3 billion years ago.
Ladies and gentlemen, we have detected gravitational waves. We did it. I am so pleased to be able to tell you that.
So that was the great announcement, and you can see this. They put out a paper in Physical Review Letters. There very kindly they give reference to the paper I had written long ago, that is 45 years ago. So what is happening is shown here graphically. See, there are two black holes which are inspiraling. They are waltzing around and coming closer and closer. As they do that, the frequency of rotation also keeps increasing, and similarly the gravitational wave frequency goes on. This is called chirp, like that of a bird, and also the intensity goes on increasing because they come closer and closer and more gravity waves are finally they merge. And now it is static. All around here is dynamic, the inspiraling. And then they merge and become a black hole. So when they have just a black hole sitting there doing nothing, how do you detect it? And there, the only telltale signal that comes out is what came to be known as the quasi-normal modes, which it was my good fortune to discover in 1970, and that is the quasi-normal modes. It goes down and then black hole is sleeping, eternal. So you can't find it by itself, but only circumstantial evidence and so on. So they give here all the details and so on. And this is the quasi-normal modes. And it was also called, it is called in a very poetic way, the ring down of black holes. Ring down means, somebody said that very poetically, that it is like the pure, the dying note of a bell that has been struck. When you strike a bell, the frequency will be the same, but the loudness keeps going down, and so this is also like that. Therefore, it's now popularly known as ring down and not quasi-normal modes anymore. And this is the Nature paper, and you can see at the top. See, in those days, the computers were very crude. With the computer I had at my disposal in the Institute for Space Studies, this is the best I could get at the top. But later on, many people have done it more sophisticated, and we have produced a template, and they also, this was a scattering thing. It's all theoretical calculation. Gravitational waves are scattered off a black hole. In those days, both black holes and gravitational radiation belonged to mythology. They were mythological objects because nobody had seen it, nobody had believed it, very few believed it. So that is what had happened. But then of course, with the, this is on the left hand side is the one taken from Nature article, and on the right what LIGO people have put in. You can see clearly the two are there because LIGO had the two, and you can see if you make it more sophisticated, you will get exactly what they found. And that was a very euphoric moment when I did this calculation. There was tremendous euphoria for me because it was very fortunate to find a signal that characterized the mass and mass of the black hole. So that's what LIGO found, and this is what Professor Balayer will show you more spectacular thing. But anyway, this is the simulation. It's not what they saw. They saw computer simulation of the two black holes coming closer and closer, merging into one, and when they merge the quasi-normal mode. I don't want to take, but he is going to show you more. And this is the merging, and now you can see the gravitational waves coming, and the black holes are coming closer and closer, gravitational waves are coming. And finally, I would like you to see the quasi-normal modes come bunched together. You see now they are coming in a very rarefied manner. At the end, the quasi-normal modes come when they collide. Just watch. No, this is the quasi-normal modes. Okay, so you have seen the whole picture, and that is it. So I have given you a very brief outline of the history of gravitational radiation. Joe Weber's inspiring initial, very difficult thing, one quotation from him. Joe Weber used to tell us, it's only the dead fish that float down the stream. It's the live fish which swim against the current. That's what he was doing. We should all take inspiration from people like that. Compared to Einstein and so on, we are nothing, not even zero, minus something. But the little thing we can do should be also be worthwhile. And you know, people, the great quotation, I'm sorry, I have one more minute. Newton said, I can see further because I'm standing on the shoulders of giants, like Galileo and so on, Archimedes. But a 4th century Roman philosopher said, Lucan, we can see further than others, even if you stood on the shoulders of dwarfs. So we are the dwarfs, and people can stand on our shoulders. Thank you very much. Thank you.
This is the sound of two black holes colliding and merging. Where did this sound come from? A long time ago, in the distant reaches of the universe, two black holes, each about 30 times as massive as our Sun, were locked in orbit and spiraling in towards each other. The only visible traces of this spinning cataclysm would have been the way their gravitational fields warped the light of distant stars. Even as they collided and merged, there wasn't a flicker of light to be seen. The real and very violent action in this system was in the form of gravitational waves, ripples in the very fabric of space and time. These waves were constantly draining energy from the black hole orbits, leading to their ultimate collision and merger to form a single black hole. At that instant, the power of the gravitational waves was 50 times greater than that of all the stars in the universe combined. That pulse of gravitational waves, lasting only a fraction of a second, expanded through the universe, passing unimpeded through countless galaxies. About 1.3 billion years later, it reached Earth. Gravitational waves alternately stretch and squeeze space itself and everything they pass through, but the effect is minuscule. Their effect on Earth here has been vastly exaggerated to help visualize something that is otherwise invisible on this scale. To detect them and directly measure their properties, scientists built LIGO, the most sensitive measuring device ever made. LIGO uses a device known as an interferometer to measure the tiny displacements in space. In this simplified representation, a laser beam is sent towards a partially reflecting mirror and split along two paths. The beams travel along the 4-kilometer arms and reflect back towards the central mirror, which recombines them, directing their light to a detector. As the gravitational waves pass, the distance between the central beam splitter and the end mirror stretches along one arm and compresses along the other. This changes the time it takes the light to travel along the arms. The recombined light waves shift with respect to one another and produce a signal at the detector. Incredibly tiny stretching and squeezing of space can actually be measured directly in this way. How little does space distort to make this signal? Let's zoom into a hydrogen atom until we reach the proton at its core. LIGO is so sensitive it can measure changes in distance as tiny as 1,000th the diameter of a proton. And this tiny measurement, made by LIGO, was the final step in a journey that began 1.3 billion years ago in the distant universe when two black holes collided.
So what I thought was I will try to explain a few things more by using regular slides. So one of the first things you have to sort of understand is that when we try to measure the physical effect of gravitational waves, what we have to keep in mind is that Even in Newtonian gravity, we know that one of the effects of gravitation is that it causes tides on the earth. So this is a very important effect, and the reason you have tides is basically because the gravitational field on one side of the earth and the other side of the earth, they are not the same. There is a difference between them. So what is shown here is that if you really want to measure a gravitational field, then you basically cannot just look at one particular object. You basically look at two objects, because when they fall under the effect of gravity, because this is closer, this will fall faster, this will fall less, and therefore if you monitor the separation between them, that separation will increase. You can either keep these bodies in a vertical direction or you can keep them in a horizontal direction. Monitoring the separation between two bodies is the way you can decide whether there is a gravitational field or not. Why do you need two bodies? Because if there is only one body, you can always sit on that particular body and fall with it. You can do a free fall, and therefore you can transform away the gravitational field. But if you have two of them, there is a difference on those two bodies, and therefore anytime you want to make a measurement of the gravitational field, you basically try to use two bodies and measure the separation between them. Now, this basically is what he was explaining to you, you do when you use a laser interferometer. So what is shown here is that if you have a laser interferometer has two arms, and if gravitational waves, if you look at the fringe system which is produced by this, then what you do is that when there is no gravity wave signal, you set up the experiment so that the experiment is located at what is called as the dark fringe. So there is no light coming out of this particular, in this photodiode. Now as I told you, if a gravitational wave falls on this particular object, it creates a tidal force, and therefore what happens is that one of the arms gets squeezed, the other arm expands, and therefore originally there was no path difference between these two paths, but now because of this difference in paths, there will be some light which will come out of this photodiode. And what this laser interferometer experiment really does is looks for this photodiode output and then says that, well, if I can measure this, I can say whether a gravitational wave is falling on this interferometer or not. And that was what was shown to you on that, in that particular animation which I showed you. Now the question which you will ask is, if you ask for how much is the separation between these two objects, you can see that there is a small displacement which happens here. So if you want to measure a gravitational wave, what you really have to do is try to see whether you can measure that small displacement which a gravitational wave will cause on a physical system. Now when you use Einstein's theory and ask for what will be the strain, this ratio of delta L by L is called as the strain. How much is the strain if you have a very massive neutron star which is in the nearest cluster of galaxies? Then you find that the strain which you will have to measure is something of the order of 10 raised to minus 21. Now, if you ask what does this translate to in terms of displacement, the displacement is what he told you at the end, a very, very minute displacement. A displacement which is 1,000 the size of a nucleus. And therefore, it is not a surprise at all that even though Einstein predicted this in 1916, it has almost taken us 100 years to actually make a detection, because the technology required to measure such a small displacement was not available till almost the last year. So what do people do? As I said, the best way to measure small displacements is by using a Michelson interferometer. You can build interferometers which are a few kilometers long, but even that is not sufficient. So what you really try to do is try to increase the optical part by having what is called as Fabry-Perot cavities. You have an interferometer which is a few kilometers long, but if you make the light bounce in it for about 300 times, it's like building an interferometer which is 300 times bigger. So by using these kind of techniques, by using the light which is coming out of this particular port and recycling it, you can make the accuracy of this interferometer so much that you can not just measure separations equal to one fringe width, you can break the fringe or can disperse the fringe up to 10 raised to minus 11 times. And because you can do that, essentially what you are doing is, this interferometer is acting like a transducer. It is converting the gravitational wave strain into a photocurrent, and by using photodiodes you can measure the photocurrents as accurately as possible, and therefore you can measure very, very small displacements. So what you saw in that small video which I showed you is all these things which people have been working on over the last 20-30 years to build an instrument which can really measure 1,000th of a Fermi. Now let me try to explain a few things about what is the kind of work which we have been doing in India. Now when you look at the waveform which Professor Vishweshwara showed you, basically he explained to you that if you have a binary system, this binary system, because it's emitting gravitational waves, will start sort of inspiraling inwards, and therefore it will put out radiation. That radiation will have increased frequency because it's going closer and closer, and because it is coming into strong gravitational fields, its amplitude will increase. That's why it's called as a chirp waveform, and what is shown here is a waveform like this. Does that mean that when you look at the output of the photodiode, you will see a pattern like this? The answer is no. The answer is that when you look at the output of the photodiode, it will look completely messy like this. If you look at the scales, you know the reason. This scale is at the order of 10 raised to minus 18, because that's what I told you is the small displacement. But there are other sources of noise on which the interferometer is buffeted. You know, there's seismic noise, there's noise because of trucks, all kinds of things, and because of that, the noise is much higher compared to the signal itself. So you are in a situation where the signal is weak, but the noise is very high. But if you go and talk to engineers, people who worked in radars, for example, during the Second World War, they know that you can use techniques called match filtering, where if you try to correlate this particular signal with known signals of this particular kind, you can find that there is a correlation. Even in this noisy data, a signal of this particular kind is hidden. I basically like to say that if you know what you are looking for, even if something is noisy, you can find it. So obviously it means that if you really want to make these interferometers work, you should be able to predict what these two black holes are actually doing when they go around each other. So calculating using Einstein's theory what the waveform is going to do is one of the activities which you have to do. And the other one is, if somebody gives you such a waveform, you have to invent data analysis techniques to really extract out from this noisy data a signal of this particular kind. And these are the two important activities which happened in India in the years something like 1990 to 2010. So the Indian legacy in gravitational waves basically are on these two fronts. The work on modeling these sources, this was in a group around me. Currently I am at ICT-STIFR. When I did this work, I was at the Raman Research Institute. And then my distinguished colleague Sanjeev Durandar at IUCAA developed all these data analysis techniques which were used in this particular experiment to really detect these gravitational waves. Did we not try to set up an experiment in India? Around that same time, my colleague Durandar really tried to set up an experimental activity in India. Unfortunately, at that time, the experiment was not funded. And therefore, we were in a situation that we had many students, we had many postdocs who worked with us. They went and worked in gravitational wave experiments abroad. Fortunately, all of them have come back and they are in faculty positions in many institutions in India. It is this community on whose shoulders we really build the IndIGO consortium. So what happened is that by 2010 we realized that the first generation detectors have achieved their design sensitivity, and if we really wanted to participate in the future in a gravity wave experiment, we really had to do something remarkable to start Indian participation in gravity wave experiments. Remember, we had only worked on theory, we had only worked on data analysis. And that is why in 2009, we formed what was called as the IndIGO consortium. We brought together people in different national labs, different research institutions, different universities, and built this consortium. As I said, the strength really came from all our students and postdocs who had come back to India. And in 2011, as a follow-up of this, we submitted a proposal to DAE and DST on what is called as LIgo-India. Now, I just go back again and remind you of something which you have already sort of seen. So what this is basically showing you, you hear at the back, you can hear a kind of hiss, right? That is like that noise. But in that noise, at the end you see a bip. That signal lasts for only about 0.2 seconds. Remember, that is the real challenge. A signal which just lasts for a very small time, but as Professor Vishweshwara showed you, from the data analysis we could reconstruct exactly what happened with that particular system. That is the amazing power of the analysis which happens with this particular experiment. And this particular plot again was shown by Professor Vishweshwara, where he explained to you what really happens. So what you really have to do is use the power of Einstein's theory to actually calculate what this waveform looks like. And my work for almost 2 decades with collaborators in France really calculated how the waveform will look like if 2 black holes go around each other, if 2 neutron stars go around each other. And then finally, this particular approximation which we use, which is called as the post-Newtonian approximation, breaks down, and you have to replace it by more sophisticated methods like numerical relativity. And then finally, as Professor Vishweshwara explained to you, that you see that there is this ring down. So Einstein's equations can be completely studied to predict this particular waveform, and the information which comes from here plays a crucial role in detecting this signal, characterizing this particular signal. Because you asked me, how do I know that there were 2 black holes of about 35 or 40 solar masses which went round and have now become a black hole of about 60 or 70 solar masses with a certain angular momentum? All that is only possible because Einstein's theory tells you very precisely what should happen when you have a system like this. We have detected this particular gravitational waves, but do we know where the source is in the sky? So what you have to do is not only look at that signal, you have to try to understand that particular signal and try to see where is it localized in the sky. And when you try to do this analysis, you find that the source can be anywhere in this banana-shaped region. This is a very big region. It's about 590 square degrees. So if somebody wants to find out whether there is some optical emission or there is some neutrino emission from this by using some well-known telescopes like the Fermi or an astrosat or something like that, it's not very easy because it's a very large region in the sky. So the important point is that if somehow you could make this region smaller, then you will be able to locate and understand what this actually source is. So that is what requires you to set up a worldwide network of gravitational wave detectors, and that is exactly was motivated by the setting up of LIgo-India. So basically, I told you that in this discovery paper, there were significant contributions, and in the actual analysis of the event itself, the group at ICTS, my young colleagues, really played many important roles and actually contributed to the analysis. So it is an area where we had head start and we have made useful contributions. Now let me just go to the fact that the detection has happened, but that is just the beginning of the story. Eventually, what we want to do is do astronomy, then do astrophysics and cosmology, and finally also start say something about basic physics. And all this is really possible basically because unlike electromagnetic signals, gravity waves are not affected at all by all the intervening matter. It gives us information which is not accessible to electromagnetic astronomy. In this particular case, you are looking at these 2 black holes when they are merging. So you are looking at a strong field regime of gravitation. And the important thing is, even if you had a different theory of gravity, which is not Einstein's theory, it will predict gravitational waves, but the properties of these gravitational waves, how fast they will propagate, how many polarization states they will have, it can be very, very different, and that is how you will be able to probe basic physics by using gravitational waves. And as I told you, finally, there is a multi-messenger astronomy which is emerging, and for that you really need to localize sources very well, and that is exactly where our project really comes. Because today we have these two detectors in the US, there is also a detector in Virgo, but the Americans realized that since they had two detectors in the same beam tube, if they could move this detector to a location very far away from US and Europe, then immediately you would have a big advantage. And simulations basically show that if you had a detector in India, this angular resolution improves by factors of 10 or 20. It's not just an empty statement. If you really do the simulation, you can see that if you put the two detectors in the same beam tube in US, these sources are not well localized, but that same detector, identical detector, just moved to India, immediately all over the sky. Sky localization is excellent, and we can do multi-messenger astronomy. What is shown here is that if LIgo-India were active, then the sky localization would be so much better. It makes a factor of 100 difference. So you can see that having three identical detectors in the international network immediately breaks this particular region into a very small region. So if you have a sophisticated telescope, it can look for follow-up events in this small region. It is not possible to do it when the region is so large. So what is the status of the LIgo-India project? As you must have heard in the newspapers, we received on 1 week after the discovery, 17 February, we really got our in-principle approval. So the project is about to sort of start. So what is our dream? By 2023, there will be a global network of detectors, a detector in India also, which is a clone of the advanced detectors which are there in the US. Now, Professor Rao always asks this particular question. There is no point in just doing things which other people are doing. There has to be something which has to come beyond the experiment which you are going to do. So it is a detection, it is astronomy, but what else will it give us? So what really excites me, even though I am a theoretician, is the fact that this experiment involves technologies. And as somebody at the National Science Foundation said, every single technology they are touching, they are pushing, and there is a lot of different technologies they are touching. It is this fact which I think is going to give us the big advantage. Because if you look at the interfaces with technology in this particular experiment, you will see that though we begin from basic physics, the interface with precision experiments at the foundations, at the frontiers is very, very high. And it involves technologies which are at the cutting edge. And it is this which is going to have the advantage, because people who will work on this particular project will have expertise, will gain expertise in this. The next generation things will involve research in these particular activities, and we think that therefore this experiment has the potential to really affect other branches of physics, other branches of experimental physics, other branches of instrumentation, and therefore, even though I am a theoretician, this is what excites me. So basically now, let me just tell you that just as we have a very big astronomy all the way from optical to radio to other branches like gamma ray and X-ray and so on, the gravity wave sky also extends over about 2 decades. And the detection is just the beginning. Eventually what will happen is that there will be detectors in space, there will be pulsar timing which will look for gravitational waves at other frequency range, and eventually we will be able to even look for gravitational waves from the Big Bang. Since Professor Rao is involved in space, I wanted to point out to him that at this particular point there is a very exciting technology mission called LISA Pathfinder which is happening. This technology experiment is really going very well, and we think that if this is successful, then the era of the space-age gravity wave detectors will also come about. So let me just conclude with a few things. Over the last 10 days, many exciting things have happened. So with advanced LIGO, we achieved the technology to make the direct detection of gravitational waves, as I told you, 100 years after Einstein predicted them. We also have corresponding progress in the two-body problem in general relativity to detect gravitational waves. We can characterize them, and as was shown in this particular paper, you can even test general relativity by looking at these particular predictions. The direct detection of gravitational waves came from a binary black hole system. Chandrasekhar worked both on gravitational waves and on black holes. So in a sense, he's doubly right when he said that astronomy is actually the true home of general theory of relativity. As Vishu's discovery basically shows that black holes really ring down, as Vishu had guessed and proved in 1970. In principle approval of LIGO-India, the global network now will be extended, so we can provide localization which is required for multi-messenger astronomy. And as I wanted to add, if LISA Pathfinder succeeds, it will lead for a possibility of a gravity wave detector in space. So we can see here that a new window to the universe is actually about to open, and though people like me will not be around, all the young people in the country have a lot of things to sort of look forward to. So thank you.
My name is Ramaswamy. Since the gravitational waves are so weak, something really stupendous like two black holes merging has to happen. How often does this happen? Is it just luck that in the 1.3 billion years we happen to be at a time when this happened? Or is it a common occurrence in the universe that in the next 100 years there is likelihood of detecting more of these waves?
So the answer is that, when you go for a project like this, you basically have to make an estimate based on the physics and the astrophysics what are going to be the event rates. So based on the astrophysics, people know that the kind of sources we can look for are two neutron star binaries, a binary made up of a neutron star and a black hole kind of binaries. And our astrophysics of stellar evolution basically predicts how many of such objects are going to be there. There is a big uncertainty in this. It can be as small as 1 per year, or it can be as high as 400 per year. Now, therefore, yeah, so it is 1 per year basically because of the fact, as I said, that we have come to a sensitivity where we can see to very large cosmological distances. So we have only seen one particular event, but the whole point is that as the detectors keep running for more and more times, looking at for how long the detector has been running, how much far you can see, a more precise answer to what you are asking will happen. And that cannot happen without doing these observations, because from the theory we can only say it lies in this particular range. So that is the start of answering this question which you want to ask.
Chetan from Times of India. I just have this question on what is the kind of importance of discovery of gravitational waves in relation to pulsar astronomy and vice versa.
Yeah, so two things, and I don't know what you mean by pulsar astronomy. So one important point is that, as I told you, binary pulsars are also sources of gravitational radiation. And then by using an array of these pulsars, there is something called the pulsar timing array. That will help us look for gravitational waves in a different frequency band. So as I told you, the gravitational wave band runs over 2 decades. We are looking at gravitational wave at high frequency on the Earth. Then there's a space detector. And then these pulsar timing arrays give us information about gravitational waves in a different frequency band. So that is what will happen over the next, let's say, a decade or so.
I think it's less.
So you said that when you had proposed the gravitational wave detector experiments while at RRI, they were not...
No, not me, Ayuga.
Your group,
yeah.
right. but they did not get the required funds. However, LIgo-India has been approved now.
Yeah.
Do you think there's been a change in research policies from the government?
I mean, things that, for example, at that particular time, people assessed that we didn't have enough, the funding was not sort of justified, there was not enough expertise. So over the last 20 years, I think the general scientific experimental expertise in the country has improved, and therefore, obviously, things are considered more serious, taken more seriously now. And as I told you, over the last 20 years, we have built a community. We have established our credibility in the international community. The international community is willing to collaborate with us and put a detector in India. Remember, all big projects, we have always participated, but those projects always have been outside. So the fact that we have established our credibility, which is a long haul. For example, the space program, as I said, has established its credibility. So when the space detector for gravitational waves will be discussed, I hope that ISRO would also would be in discussion with NASA and ESA to contribute to this particular project. So I think over the last 20, 25 years, all this performance which has happened in ISRO has put us on a map, and we have to make the most of it. If we sit back, I think we'll never get there. So we have to take up those challenges, and we can do it. We have to have faith, we have to take risks, but unless we do that, we'll never get there.
In fact, the interaction between ISRO and the NASA is just now going on. It just finished probably today, and people from jet propulsion.
A very simple question. What was, you being directly involved with the LIGO project?
Yeah.
What is the impact of, Professor Vishwara's work, in discovering gravitational waves? I want to know from you.
So I don't know exactly what your question is. Maybe, we can talk, I can talk in more detail.
Later.
I can be outside and we can talk about it. But the basic thing is my own work related to modeling these waves which come out of black holes or neutron star binaries. You have to use Einstein's equations and calculate what is exactly, how does the wave look like. And that is really what was contributed by my group to this particular project.
I think you can do it.
One last quotation, because he said things to do with gravitational waves, how weak it is and how difficult it is. Even before or at the time Weber was trying to see, there was this Professor John Wheeler, who was an inspiration for many of us to take up general theory of relativity. My thesis advisor was Charles Misner. His thesis advisor was Wheeler, and he was a co-author with Niels Bohr, and he had a lot of interaction with Einstein. So my own lineage goes back to Einstein and Bohr. Okay. Now, when all this was going on, in one of the meetings, Wheeler said, the gravitational waves are so weak. Technology may never catch up with it and it may never be detected. That was the feeling he had said. And he said, how do I put this in a way that, it is telling, not the same that technology. So apparently he went to a Chinese restaurant before coming to the meeting, and in Chinese restaurants, at least in the US, they give something called fortune cookies. You open it and there is a slip of paper which gives you your fortune. So apparently he opened and there was this quotation. If it came true, it wasn't much of a dream, was it? So he said, if the detection of gravitational wave came true, it wasn't much of a dream. Fortunately, it wasn't much of a dream. It has come true. So I want to. Thank you very much.